Hey, Aapo, you haven't happened to see my Fundamentals of Radio Engineering? I can't seem to find it anywhere.
Well, I don't know. I think someone might have put it back in the bookshelf.
I'll go check it there.
Sometimes in life, you come into a situation where you need to find something quickly. A such case could be locating a single book. However, sometimes the task might seem overwhelming and too time-consuming. Books might be stored in various places like offices, lounges, and meeting rooms around the department. One possibility to ease this situation is to use RFID technology. To solve this problem, the Aalto ELEC team developed a RFID-based book locator system. The goal was to manufacture the system affordably with off-the-shelf components. A RFID system consists of a reader and a tag. The reader sends simple commands and a carrier wave to power the passive RFID tag. The tag responds by modulating the carrier wave. The benefit of RFID technology in this application is that you don't need a line of sight to the target. Ultra-high frequency band RFID systems provide enough read range to successfully read the tags from a distance of several meters. In this project, the main difficulty was to design a RFID tag to operate in varying environments. The differences in book size and paper quality affect the impedance of the antenna and might significantly detune the tag. Thus, the tag has to be robust by design and take these differences into account. A suitable tag was designed using an electromagnetic simulator software. A meandered dipole antenna was used as the starting point. Due to high capacitance of the RFID chip, the antenna was required to be highly inductive to achieve conjugate matching to the chip and to maximize power transfer. For the antenna to be robust and work in different conditions, a wide impedance bandwidth was needed. A new method of adding several tunable inductance loops in the antenna structure was developed. By adjusting the size of the loops and distances between them, the antenna impedance could be easily tuned to conjugately match the chip impedance. The double resonance of the antenna enabled a wide -10 dB impedance bandwidth of 90 MHz. The wide bandwidth prevents detuning caused by uncertain permittivity value and book size. After the simulations were ready, the tag was manufactured using the available equipment in the lab. The schematic of the antenna was printed on a transparency and exposed to UV light to soften the photoresist on the substrate. Then the PCB was developed and excess photoresist was washed away with diluted sodium hydroxide. After that, the tag antenna was left in an etching machine to remove the copper around the antenna traces. Finally, the RFID chip was soldered to the RFID tag antenna. The performance of the final tag was measured with a RFID tag measurement instrument in an attenuated measurement box. The performance was measured with several different kinds of books and paper material surrounding the tag. The threshold power at which the tag responded was measured. After the designed tag was found to be operational, it was time to focus on the RFID tag reader. The reader was constructed from several off-the-shelf components. A cheap Raspberry Pi computer was used as basis for the reader. A RFID module was used as the radio transceiver. LCD screen, lithium polymer battery, and a 3D printed case were added to the design. Different parts were connected with an interconnecting PCB and were fitted in the enclosure. A patch antenna with a gain of around 5.5 dBi was designed for the reader. The gain was designed to result close to 4 watts of equivalent isotopic radiated power with the 1 watt output power of the RFID module. Circular polarization was used to be able to detect books oriented in different directions. The software of the reader was programmed with Python and it communicates with the RFID module through the serial port. The user interface consists of a main screen where the operating mode can be selected. In scan mode, the reader searches for all books in the reading range. In the library mode, a specific book can be searched. After the whole system was ready, it was time to test the performance. An anechoic chamber with a directive measurement antenna connected to the reader was used to minimize reflections. Reading ranges as high as 5 to 7 meters were achieved. Now the reader was ready for some serious scanning and assist our guy in need.
Psst. Here, try this.
What's this?
It's an RFID-based book locator.
Oh, neat.
Yeah, please turn it on.
Hey, I found it. Thanks, guy. You really saved my day.
Hey, what's this noise? It's getting kind of annoying.
Sorry. My bad.
This project was designed by the Aalto ELEC team. The team consisted of 2 first-year students and 2 senior students. The work was done as a part of a practical antenna design course and proved to be highly educational. The team would like to thank you for listening.